Welcome to Hydrology. We continue our discussion on routing of flows from storm events through channels. Today we're going to talk about stream stage inundation flows. This is Chapter 11, Lecture 1. I'm Dr. Marty Matlock. Let's get started. Our reference document is the National Engineering Handbook, Part 630, Hydrology, Chapter 13, Stage Inundations. Remember, we're talking about the water balance here, the hydrologic cycle and the water balance, and the movement of water across the landscape. One of the major challenges we have with water moving across the landscape, there are time lags. There are initial abstractions, evapotranspiration, infiltration, but then this thing called change in storage. It really is about how water is stored on the landscape as it moves across the landscape. And we spent some time in earlier chapters talking about water storage on the land in the soil and through infiltration, and then also through small soil indentions. Here we're talking about channel storage, the storage of water in these flow conveyances. Now, flow conveyances are geometric shapes, and they have width and depth, and they have a wetted perimeter and a cross-sectional area. They have a deepest point. These channels can be 6 centimeters deep, or they can be 6 meters deep, or 60 meters deep. But they all have similar characteristics. Water is flowing through them, and the flow of water has similar processes. The flow depth is the distance between the channel bottom and the water surface. So this is pretty intuitive. That's how deep the water is. We measured at the deepest point, the Thalweg, which we discussed earlier, is the valley way in German. For rectangular channels, the depth is the same across an entire section because it's just a rectangle, it's a box. But it obviously varies in natural channels. Depth is often measured relative to the Thalweg or lowest point. The normal depth is the depth of flow in a uniform channel for which the water surface is normal or parallel to the channel profile and energy slope. It's flowing down the energy gradient perpendicular to topography. Flow, which is Q, is measured in cubic or L3 over T, length time to the cubed over T, which is cubic meters per second, or cubic feet per second, or cubic kilometers per day, through a cross section of stream, and we measure those looking downstream from the left bank to the right bank. So we see that's A to A prime. I'm sorry, this would be looking downstream, A to A prime, left bank to right bank. The prime is usually the right bank, is equal to the velocity L over T times the cross-sectional area, which is L2, from a dimensional perspective. And that's how we get L3 over T. As water moves down a channel, it can move through several processes. Translation of a wave is the downward movement of a wave without changing the shape of the wave. This process is dominant over short distances in narrow channels. Attenuation of a wave changes the shape by reducing the peak and extending the base. And this is more common. Translation of a wave, really, it only occurs under very specialized conditions. Attenuation is the most common impact of flow. A flood wave in a river channel is subject to water storage in the banks, translation of a flood wave downstream, and attenuation of the flood wave as the channel opens, which creates a sort of a modified discharge curve where you see both attenuation and translation. And that's certainly, as rivers get larger, this is the more common phenomena. In profile, this water is moving down an energy grade line. And that grade line is measured by change in height and elevation from the overall system, which is measured, which we call head or head energy. The water surface may have some nonlinear characteristics associated with that translation of a wave. The channel bottom certainly is not linear, so you have multiple characteristics across some standard datum point. You have the upstream height Z2, the downstream height Z1 of the bottom, the downstream height Y1 and upstream height Y2 of the water surface. And then you have the energy gradient, which is alpha V squared 1 over 2G On the downstream, upstream, it's potential energy, alpha V squared 2 over 2G. And of course the headspace. So this is the representation of the energy equation for flow in a channel. Total conveyance and velocity for cross sections of a stream require that the flow be divided into units of uniform velocity, because the channels are not, unless they're human-made and constructed out of relatively non-transferable materials, that is concrete or rock or sometimes vegetated channels, the channels are typically not uniform. They're subject to erosive forces, and they're shaped by floods over time. So we have the main channel in the middle, and then we have overbank channels. So the banks would be at the edge of the main channel. The main channel would be at a certain depth, and then once water depth exceeds the main channel depth, it moves into the overbank channels. And the overbank channels have different characteristics. They're divided into the widths with common Manning's end values based upon the land cover. So you might have gravel material in the main channel. You might have vegetation on the overbank channels immediately, and then the upper overbank channels you might have trees, riparian zones. And so those would be divided into separate sections and then analyzed with an area weighting. It's fairly straightforward. Q equals Ks to 1/2 to the F. In this case, where K equals 1.489 over Manning's N times AR to the 2/3. And A is area for the subdivision. R is the hydraulic radius for the subdivision. That's the wetted perimeter. The wetted perimeter is the part that's touching the water. And S sub F is the slope or the energy grade line. So you calculate these areas, the K for each of these areas, and then you add, this gives you an area weighting for the whole system. So K for the left overbank is K1 plus K2. K for the right overbank is K3, where you have Manning's N 1, 2, and 3, and the K for the channel in the middle. And you add all of those up, and you come up with the appropriate K times then the slope of the energy grade line to the 1/2 equals Q. Remember, we talked about critical flows in previous chapters. The critical depth where flow is critical. Critical flow represents the flow where water is pushing and not gravity pulling the flow. So the mass and inertia of water above pushes the water downstream versus the gravity of pulling water downstream. Both are always acting, but it's which one is the dominant force in the energy system. So the depth D1 and D2 are alternative depths for the same energy level here in this energy level graph. So we have the same specific energy, but different depths give you different critical states. At shallow water, it's subcritical. So at shallow water, at deeper water, it's subcritical because you have enough water mass that gravity is pulling it. In shallow water, it's supercritical because the velocity of the water upstream is pushing the water down. Only one depth exists at the critical state, which is the lowest possible energy for a given discharge. So the specific energy at any cross section for a channel of a small slope, those are most natural channels, is alpha equals 1. So the energy equals Y plus V squared over 2G. Y is the depth. Water resource planning requires tabular plotted data showing the relationship between the area inundated and stream stage discharge flow and frequency. You got to know where the water is coming from and where it's going and how it's moving, especially during significant rainfall events. These types of data are called stage inundation relations and are often used in the economic evaluation of justification for a flood control project, an irrigation project, or other projects. So as engineers, we have to be able to show the value of the project in terms of stage inundation. That is, how stage changes with flow. The information is developed using data obtained in project field surveys. We're getting a whole lot better at being able to collect this information using remotely sensed information, especially with LiDAR and digital elevation models, which we're using in HEC-RAS extensively. Different planning efforts require different levels of accuracy and detail in stage inundation relationships. So the expected use of the information should dictate the preferred analysis technique. The way you collect the data depends on why you're using the data and how. Many stage decisions focus on acres flooded in a stream reach to the stage somewhere along the length of the reach, generally at the downend stream. Stage inundation relations show the number of acres flooded at different depths appropriate for particular analyses. Now, when we say acres flooded, these are often the sort of upper banks in the floodplain, not necessarily the landscape per se, though it can be. The simplest case occurs when one cross-section is used to represent conditions in a reach. This stage area inundation relationship is considered a simple case. So let's talk about these simple cases. A sample computation of a stream stage versus area inundation for a cross-section. Where we have stage, we have 4 columns here. We have stage, which is the height of the flow, 4, 6, 8, 10, 12, 14. We have cross-sectional widths, 24, 92, etc. As the water gets deeper, the cross-sectional width gets much larger because the floodplain opens up. You have the width minus the channel width. So we take out the channel width, which is 24 here. That's the first stage. And so all of these widths now are the widths of the out-of-bank area. The inundated area in reach, that's the length times the width of the out-of-channel area. That's pretty straightforward. So the length of the section, and so the reach is 8,640 feet long. And so we know that divided by how many feet are in an acre, and we multiply that times this channel width, and we get how many acres are inundated. Pretty straightforward. This is just the area converted to acres of the out-of-bank channel. So we can look at these under computation of stage versus area inundated at selected depths of flooding. We can look at total inundated acres now, and the acres inundated at various depths. And so this is just a simple step function that from 0 to 2 feet, we have a certain area inundated, and from 2 to 4, that increases, and 4 to 6, and greater than 6 feet. So this is a process for evaluating for a given depth how much area is inundated. So total area inundated at 10 feet of depth is 115.8 acres. 47 of that is in 0 to 2 feet of depth. 54 is in 2 to 4 feet of depth. 13 acres is at 4 to 6 feet of depth. So that's the depth of the water on the area. Another way to see these are graphically, if we look at stages in feet versus acres inundated. And so you can plot this and show the total depths, total for all depths, and then how deep the water is over the landscape. Again, a way to take a look at this is if we have cross-section of a flow here with an area flooded. And so at 0 to 2 feet of depth, we have our stream bank. So 4 foot's bank full. So at 6 feet, we have 2 feet out of the banks. So we have 0 to 2 feet of depth. That's 13.5 acres. When the stream flow is at 8 feet, then we have 4 feet's at bank full. 6 feet would be the area under 2 to 4 feet of depth. Now it's 2 to 4 feet. And 0 to 2 feet is this outer shallow area. And so it adds up. So you can see graphically, as the water flow increases, we can calculate based upon the depth of the cross-section of the stream, how much acreage is covered under how much water. Now, this becomes important because of the tractive force of that water based upon its weight, its depth, and that tractive force is erosive depending on the velocity, and that will cause erosion and damage, as well as also the damage to structures and other items of concern within the watershed. Computation of stage inundation relations becomes more complex when more than one cross-section per reach is used. You basically have to average them. So the number of acres flooded at various depths is sometimes obtained by comparing the acres between flow lines plotted on a map in a floodplain. Fortunately, again, we can do this automatically with HEC-RAS, and it's not automatic. We have to put a lot of data and time to create the model, but the model calculates these averages. Computers do that very effectively. So when two cross sections per reach are used and the drainage areas at the sections are not significantly different, they can be used using that sort of standardized approach, because we can assume that they're simple. Determination of acres flooded for given depth increments follows the procedures that we just discussed. So let's say we have two cross sections, cross section 1, cross section 2. Now areas related to the foot of the reach for each of the stages are averaged, and that's the way you come up. So the average between 41 and 30 is 35.5, and so that's the way you come up with these. You create an average cross section of the system, and that's the way we create the inundated area in reaches in acres. Not complicated, just tedious. That's what we do. That's what spreadsheets are good for. Now, sample computation of stage versus area inundation with two cross sections in the reach and drainage areas at sections that vary significantly are a little more complicated. So we have here at stage 1, we have 720 cubic feet per second with a top width of 41 feet and 680 cubic feet per second with a top width of 32 feet. So an average top width, we take the average of the two top widths. We have channel width and inundated areas at bank full are 0. Then as we move out of the bank, we subtract. Again, we subtract the area from of the stage from the bank full width, and that gives us the out of bank width, and then we average those, and we come up with our average top width minus channel width, and we come up with inundated area in acres. And the acres is just taking the width in feet times the length in feet and divided by 43,560 square feet per acre to come up with acres. Meters and hectares are a lot easier. 10,000 hectares or 10,000 square meters in a hectare. It's 100 meters by 100 meters. Makes life a lot easier than acres. So, sample computations for stages versus inundated with 3 cross sections and drainage areas are not significantly different. You're just averaging all 3. I don't really see why you would do this. You would just usually define the reach as between the 2 cross sections, and then just keep moving down. But if you have to collect them or aggregate them, you just keep averaging. This is not complicated. So we ended up with this flood damage reach based upon inundation, where you can take the head of the reach, which is the upper reach, and the foot of the reach, the bottom, and then you can do the midpoints, sections all the way down with cross sections, and you can come up with averages. So the links then become the midpoints between the two. So the links for A are A up and down. Links for B are midpoint between A and B, up and down. And so this is why you come up with how you come up with the links. Now, the equivalent way to do that is just to call the distance between the lower reach and the next upper reach as your average length. Just be consistent with how you manage this. Where that gets to be a problem is so you would have a G to F length and F to E length. And the reason we do these half lengths is because we're not really measuring what's coming into A. Just A is our starting point and G is our ending point. And that's why we end up doing these half lengths. We have a number of web resources for you to review. The chapter is available particularly, but we've got, as we move into channel design, this inundation mapping and inundation curve becomes critically important. Thank you for